Hi, my name is Peter Buck. I work for Siemens EDA as Director of Product Management for Mass Process Correction and Mass Defect Management. Today I would like to present a justification for a new integrated circuit layout standard to meet the requirements of curvilinear masks and the formation of a new semi-task force to cooperatively create this new standard. The universe, as we know, is curvilinear. But since at least the 17th century, when René Descartes invented Cartesian coordinates, humans have described the world with rectilinear approximations. In the world of IC manufacturing, design layouts and derivations of them modified with optical proximity correction to compensate for lithography and process nonlinearities are represented in rectilinear piecewise linear polygons. As the complexity of OPC has increased to resolve smaller and smaller features, rectilinear approximation of the post-OPC patterns struggles to provide the expected feature size and process window benefits, at least without significant pattern complexity. A simple illustration is the comparison of the imaging of a square and a circle with the same area. The circle will produce better nils and image contrast. In 2004, Luminescent published an approach they called inverse lithography technology, or ILT, as a method to actually create curvilinear structures, although they were still represented as polygons. Luminescent was able to demonstrate that improved process window was achievable. Unfortunately, the variable shape beam mask writers in the predominant use at the time still composed mask patterns using rectilinear and right triangle shots, which meant that the shot count exploded. Since VSB write time is primarily a function of shot count, VSB write times were impractically long. In 2009, Samsung looked at the simplification methods to see if it was possible to find a solution that produced acceptable write times and a reasonable process window improvement, but concluded that by the time simplification allows for acceptable write times, the value of curvilinear in terms of process window was lost. Siemens, then mentor, realizing that the mass process blur would round corners, wondered if this would in effect recreate the curvilinear intent. But while this was shown to be true, the full process window benefits of real curvilinear couldn't be achieved. Multi-beam mask writers came to the rescue. Grayscale raster writing makes write time independent of pattern complexity, while massive parallelism increases area coverage rate, resulting in reasonable write time independent of mass pattern complexity. Finally, curvilinear OPC output can be made manufacturable. Except, as mass complexity increases, so does mass data volume. As shown in this graph from Samsung, mass data volume has increased almost linearly through the single patterning era, starting to flatten out as the increase in K1 slows, followed by a flattening in the multi-patterning era, where the number of masks per device increased, but data volume was capped by K1, to a 5x jump entering the EUV era, as EUV masks make single patterning possible again. The prediction for EUV ILT is expected to create a further jump in mass data volume, which creates cost and cycle time bottlenecks in OPC, MPC, mass data prep, mass data file transfers, and potentially mask writing itself. The last time the industry had such a problem was in the early 2000s. The venerable GDS2 format, which had been used since the 1970s, had finally run out of steam. The industry formed a semi-task force in 2001 and ultimately released a new format, Semi-P39. The goals of the task force included achieving a better than 10x reduction in file size compared to GDS2 stream, efficiently handling flat geometric data including arrayed geometric figures, removing the 16 and 32-bit restrictions allowing integers to extend to 64 bits and beyond as required, enhancing the overall richness of information contained in the format, and to make the format publicly available to academic and commercial entities. GDS2 was widely used but privately owned. It is interesting to note that in a July 2001 workshop, a multi-vote of the attendees put file size as the most important problem to solve, and while curvilinear shapes was on the list, it was low in priority. Curvilinear was recognized as a potential future problem, but not a current problem. A circle record type was ultimately added to P39, but circular ends to paths were removed. P39 was well conceived, and its innovations, including the use of point lists, modality, variable integer length, coordinate offsets, implied last coordinates, 64-bit compatibility, and extensibility through the user-defined X records and through the revision process as an active semi format, have allowed P39 to serve us well in the ensuing 20 years. To solve the new data volume challenge presented by curvilinear layouts, the industry is once again working together to form a semi-task force to repeat the success of P39. Based on the observed data explosion as curvilinear OPC methods are introduced, a new informal task force was formed in late 2019, driven by Samsung, TSMC, and Intel, with representation from Siemens, Synopsys, Nippon Control Systems, D2S, Acelta, and ASML Brion. One pre-COVID face-to-face meeting was held in January 2020, followed by several virtual meetings to converge on a path forward, the latest on May 27. Initial goals of the task force include quantifying the curvilinear data volume problem, developing, testing, and implementing newer revised formats based on P39, and formalizing the working group as a semi-task force. Formal documentation to create the task force has been submitted to SEMI and will be reviewed at the next meeting of the North America chapter of the Microlithography Global Technical Committee on July 14. We don't have to reinvent the wheel. Curves have been represented in various ways, apparently since the 18th century. Wooden splines were and still are used to draw smooth curves for boat design. In the 1960s, Pierre Bézier defined curves for bodywork at Renault using polynomial functions. 2D and 3D curve functions are used today for computer graphics, automotive design, model-based systems engineering, and more. Members of the task force have started to look at these data volume reduction opportunities for various approaches to curvilinear representation and to consider how these could be implemented in a production flow. To illustrate the focus of the ongoing work, I will refer to two 2021 SPIE advanced lithography papers, one a joint effort by Samsung and Siemens to understand the benefits of various curvilinear approaches in terms of file size reduction and the impact on the mask as a function of curvilinear fitting tolerance, and a second paper by Siemens that drills down more deeply on curvilinear representation. With Samsung, we tested 4 approaches to curvilinear representation. 2 of these are polygon simplification approaches that reduce the number of vertices in a systematic manner and still allow P39 to be used without modification. Bézier and B-spline approaches were also tried. To be able to evaluate these, we had to first fit the input polygons to Bézier and B-spline representation, then convert back to P39 polygons with high-frequency sampling to compute shape accuracy. Fitting tolerances from the conversions were sampled from 0.1 nanometer to 2 nanometers at mask scale. An EUV mask was manufactured by Samsung, and SEM images taken and CD measurements made. The CD measurements of the fitted curves were compared to the input polygons for 6 different shapes. The results showed that on average, the impact on mask CD compared to baseline was within 10%. File size compaction ranged from no compaction up to 3.3x averaged across all patterns, with compaction factors of 6 to 8x in specific cases. Since the SPIE papers were presented, EUV Ames data has been collected to determine impact on wafer imaging. That data is still being analyzed. A 5th approach to compaction was evaluated, but not included on the Samsung masks. Paths turn out to be an efficient way to represent SRAS. Curvilinear constant width polygons can be efficient with a reduction in vertex count on average of 6x and a reduction in P39 file size of over 3x. Path centerlines can be represented in point lists supported by P39 or for additional compaction by Bézier or B-spline. It turns out that the rounded path ends that are in GDS2 but were left out of P39 may need to be reintroduced. I hope this provides some insight to the challenges of curvilinear-based IC manufacturing and some of the approaches being evaluated to solve at least one of these through industry collaboration that will use the approach and knowledge gained from the development of Semi P39 to produce new layout format standards that will be similarly successful and long-lived. Thanks for your attention.